Okay, welcome back to the channel. So today I'm going to go over how I created this, I call it a structure generator. It's kind of cool. There's like three systems combined into one over here. So if I turn this off, you see this is our base mesh. And the system allows us to basically turn it into a structure that has platforms. We can do top platforms and bottom platforms as well. Also have a slider here to include these angled faces. And then we've got these structure beams, which is basically just any model that you choose being instanced on all of the edges of your mesh. In addition to these structure beams, we've got support beams, which basically crosses your object across each face of the mesh. Then there's also a pipe system that goes across the whole mesh. You can use a combination of these different systems to make different kinds of like background detail, greebles, fill out your sci-fi scenes or whatever. So yeah, let's get started on that. I'll start out by just making a simple shape. Okay, let's just go with this for now. So we'll make a new GeoNode setup. The first thing to do is to separate this into three different parts. So we've got all of our upwards facing faces, our downwards facing faces, and then everything else, which will be the sides. So we'll do this with a separate geometry node, set that to face, and we'll analyze the normal. We'll compare it to the upward facing vector, and this gives us our top faces. We can use this epsilon to grow that selection so that we catch some of these angled faces as well. And then so we've got our top faces and then the rest. So we'll add another separate geometry. We'll compare the normal again, this time to the -1 direction. And that'll give us our bottom faces over there and then the side faces over here. Okay, and remember you can add any of these parameters to the modifier stack over here so that you can make changes on the fly. I'm not going to be doing that for this tutorial because it is kind of time consuming setting up all of the panels and stuff. I already did it once, I don't want to do it again. So you can either do that yourself or just spend $3 and support me on SuperHive. Cool, so let's start with our top faces. And for this we want to basically quickly recreate the solidify modifier. So we'll just do an extrude mesh. I'll also flip the original faces, join those together, and then add a merge by distance. What we can also do is just combine these two together and then add a switch. So you can either include the bottom faces or not. I'll just turn this down. So now we have a checkbox for do you want bottom faces or not, and then you can add another one over here for do you want platforms or not. You can just set a material here as well. I'll just quickly create some stand-ins just so that we can easily see them. Cool, nice and easy. That is the platforms section. Okay, next will be the structure beams, and for that we'll start off with the side faces. Remember, we want to instance our beam model on all of the edges, so I'll just turn the mesh to points, turn the edges to points, and then we can have an instance on points node. But before I do that, let me just model a quick beam to use. So I'll leave this at the default 2 meters, and then just make some adjustments to get the shape I want. So we're going to instance our beam on these points. Now we want all of our beams to align on each edge. So what you might be used to trying is using the normal. Align rotation to vector, plug that into the vector and that into the rotation, and you see that actually does nothing. That's because the mesh to points node disregards all of this information, so we lose all of this once we convert into points. So how we can retain that information by instead capturing the normal on the edge domain and then passing that through instead. Cool. So that gives us something, but it's actually not exactly what we want. And if I just combine that sides mesh with our instances, we'll see that they're pointing outwards from that edge, where we actually want to align it to this edge like this. So the way that we can do that is, instead of using the normal over here, we're going to grab a node called the edge vertices node, which gives us a position 1 and 2, as well as index 1 and 2, and that is the position and index of these 1 and 2 vertices of every edge. So when it comes to this edge, it's going to be looking at 1 and 2 over there. For this edge, it'll be 1 and 2 over there, etc. We've got position 1 and 2, and if we subtract those two, that gives us a vector pointing from one to the other, and that's exactly what we need. So we'll take that vector, put that into the align rotation, and that kind of fixes our problem. Lovely. Now the next issue we'll see is that some of these are too long and some of them are too short. So with the same vector that we calculated pointing from the two vertices of the edge, we can then just grab the length of that vector, which actually tells us the distance between those 2 points, pop that through a map range, and we'll see we want to control the Z scale of these beams so that they fit. So put that into a combined XYZ, set the X and Y to 1, that into the scale, and then it's going to be a matter of changing these two values, the from max and the to max, to get these to work. So I'll increase the to max until this one fits the long length, something like that, and then I'll bring down I'll bring up the from max so that those fit over there. Cool, and that gives us a nice dynamic instancer for those structure beams. You can also uncheck clamp here in case you end up getting longer faces. So for example, if I turn the clamp back on and I stretch this out, you see that this is going to, it's going to hit a maximum limit, but if I uncheck that, then it'll just interpolate according to this map range function. So it'll continue stretching out with the same ratio. Cool, so now we can just join up these two and see what they look like together. We can also set our material for the beams, or actually the instance object already has the material, so that's fine. Okay, so let's have a look here. I'm noticing that my platforms are maybe a bit too thick, so I'll just bring that down a bit, make it 05. And now I'm seeing these beams. I like this one that's aligned like this, but I'm not a fan of these ones that are aligned with the eye part of the beam facing up. We've got this first aligned rotation to vector, which solves our z-axis, so we can duplicate that, pivot on the z and change this to x. We're also aligning that x value to the positive y, so something like that will work. Actually, I'm just now thinking that if we align this to the normal, that also gives us something that's not too bad. Maybe change this to the y. Yeah, I actually like this. That's decent. Oh, but then the problem is that these corner beams, they face at 45 degrees, which might not be an issue. That might be what you're after. It's actually not a bad look, so you can keep it like that. Okay, so yeah, this method of aligning the second one to the normal, that's not too bad. Although you are going to have 45-degree angles over here, your choice. But if you don't want that, then you can remove this, have them aligned to the positive z, but then add this rotation in to specify which direction those ones should align to. So I'll just change this back to x so that these top ones align like how I want them. And then this one over here you can change to specify which direction these ones face. So if I change this to 90 on the y, you'll see they'll face this this direction, the y direction. And if I put the 90 on the x instead, they face this direction. So there's some options for you. You can decide which one you like. I think in the product I went this route, but I do actually like this route of using the normal direction as well. And also you can use this x and y to affect the thickness and the width of these beams. So you can add those in as options here as well. And that is it for the structure beams. Cool, so now we're done with the structure beams. Next is the support beams, and these are going to go across each face of our mesh. Let me just give you a quick breakdown of what we're going to need to do this. It's always good, I find, to speak through these concepts before, just so you have an idea of exactly what you're trying to do, and then try to implement them. So we want beams to go across over here. So what we'll do is turn each face into a point with our mesh to points node, and then we can duplicate this point so that there's two, and then instance a beam on each of those, and then align one beam to this direction and align the other one to that direction. Also, the astute of you might realize that the center point of the face, which is where the mesh to points node will put the point, that center point isn't necessarily the center point along these what do you call these? Along these vectors, the crossing vectors. Like if I were to draw these, you'll clearly see the center point is now over here, not over there. And also the center point for this one is over here, and the center point for this one is maybe over there. So we'll also need to calculate that midpoint, move those 2 points to their respective midpoint, then instance the beams, then rotate the beams, and then scale the beams. So let's see how that gets done in practice. We'll go mesh to points and change this to faces. And then, just to make this quick, I'll instance the points immediately on those faces. Turn this back on. And then let me just combine these two together just so that I can see what I'm doing a little better. Cool, so now we've got a beam in the center of each face. So first thing we want to do is duplicate those points so that there are 2 points on every face, therefore 2 beams on every face. Okay, then we're going to need the midpoints of these opposing diagonals. To get those points, there's a bit of math and stuff, so let's tackle that now. We'll capture these attributes on the face domain, and we want to capture let's just draw this out. Let's say we've got this face over here. I'll number these face corners 0, 1, 2, and 3. And keep in mind I said face corners. That's important because that's where we're going to be getting this information from. So we want to get the position of each of these vertices. The way we can do that is I'll grab the position. I'm going to evaluate this at an index. Okay, so if I can get the index of all of these faces, then I can get the specific position for all of those faces. And remember, we're evaluating the index on the face corner domain so that it gets the individual vertices of this particular face. So the way we do that is there's a node called corners of face. So by default this has a sort index of 0. This will basically just return them as 0, 1, 2, 3 as I have it here, or it might not be specifically 0 up in this corner, like it could be 0, 1, 2, 3. It really doesn't matter, just the point is that it starts at 1 and then it moves to the next one, then the next one, then the next one. It doesn't skip any, it goes in an order, in a circle around them. So that means if I just use this node, it'll give me the corner index over there. So that means this node now has the position of this corner. And then from here I can use the node offset corner in face. So this takes a corner index, which I'm getting over there, and then I'm going to offset it twice. So if this one returns the position of this one will return the index of 1, 2 of this one here, which is offset by 2 from there. So I'll duplicate this, evaluate that index, we're evaluating the position at this new index. So now this gives me position 0, this gives me position 2, and then I can duplicate all of these and simply increase this to 1. So now this will give me position 1, and this gives me position 3. Awesome, those are the 4 vectors that I need, so we can subtract these 2 and subtract these 2. Okay, sorry, my screencast keys were off. Hopefully you are still able to follow along. Okay, so we're subtracting those two, and that basically gives us the vector direction pointing from one corner to the other and then from one corner to the other. So we can plug these in over here. I'll just call this direction 1 and direction 2. And then we'll also need the midpoints of these two vectors, so we'll need to create a new function for that. Let's say I'll take this one, separate the xyz, do the same for this, and then I'll add a combine xyz, grab these together and turn that into a node group, plug that vector out there, and now we've got a midpoint function which takes two vectors as the input and outputs a vector at the end that is in between the two of them. So we can just plug these in quickly, call that mid1 for midpoint 1 and mid2. So inside our function, the way to calculate the midpoint between two vectors is to add all of the individual components and then divide them each by 2. We'll combine all of those up together, and that's our midpoint done. Cool, so let's look at this again. Now we've got 2 points on each of these faces. If I just look after the duplicate elements node, we see we've got our points. And if I look at the duplicate index, you'll see 0, 1, 0, 1, 0, 1. So the original point is numbered with 0 and the duplicated point is numbered with 1. You can see that here where these two have the exact same position. So each of these have the same position, it's only the index that's different. That means that if I say the duplicate index, if that's equal to 0, it'll give me yes for one and no for the other. So I can use this now to control which of these vectors gets applied to which of those beams. So the first thing we can do is add a set position node, and we are basically going to be placing those points on the midpoint. I think you're going to see it most clearly on this face. For example, on this face here, the midpoint is going to be the same for both of them, but on this one over here, the midpoint could be slightly different. So let's just see how all that works together. Remember, we've got our midpoint 1 and 2 over here, so I can put this through a switch, true and false. We'll put 1 into false and 2 into true. Just remember the order that you do this, because you'll have to do it a few more times for the rotation and the scale. So switch between those two with this as my factor, put that into the boolean, put this into the position. And now we see those two moved and these stayed the same just as we predicted. Cool, so now I'll take another switch, plug this into the boolean as well, and now we can do direction 1 on top, direction 2 on the bottom, and plug this into the aligned rotation, that into the vector, and that into the rotation. Cool, and that works. Once again, we're going to have to make a decision on the alignment of these. Like as here you can see, these ones, the eye part of the beam is facing outwards, but here the eye part is parallel to the face. So we can actually capture the normal. So we can capture the normal and then align it like so. And remember, we first did the Z, so we need to lock this to the Z, and then we can decide whether the X direction or the Y direction faces the normal. So now, just as before, we're going to do the scaling. And once again, we're going to need the length of these two vectors. So I'll just draw some readouts there and add a vector math length node, which will calculate the lengths of both of those. We'll put them each through a map range node, uncheck the clamp, and I'm just going to pull these out, the from max and the to max, to a separate value node, because these two need to update together. Okay, let's put our switch, changes the float, and we'll switch between these two. Again, using that same boolean, and plug this into the Z. Remember to change X and Y to 1 as well. And then we can tweak these values to make sure that they all fit nicely. Maybe see our smaller one. We just control this, and the bigger one control this. Once again, we can control the thickness and width as well, and we'll add this to the rest of the geometry. Cool, so that gives us structure beams, support beams, and platforms. Another thing that I did in my product was to add a random value node. We're duplicating these beams twice, but we can make this be random between 0 and 2, just so that we add some more variety. Some of them have 2 cross beams, some of them might only have 1, and some of them have none. You can add all of these values into your modifier as well, so you can make those specific adjustments as you please. Cool, and then that brings us to the final step, which is the pipe network. Now I must admit that the pipe network that I have is still a little bit iffy. Not all of the bugs have been sorted out, although it works well enough to function properly, so I'll just show you how I did that. Okay, so what I will do first is add a subdivide mesh node. We'll plug the sides in over here, and this will basically just allow you to add a bit more detail on the fly. Our pipes are going to be made out of these edges, so the more edges you have, the more pipes you'll be able to have. If we keep it just like this, you'll only be able to have a pipe, for example, running up here and across here. You won't have anything in the middle here, which might be what you want. So this is an option to just increase the amount of pipes overall. Okay, then as I mentioned, we're going to be using the edge paths to curves node, and this works with the shortest edge paths node. And the way this works is you connect up the next vertex index. We need to specify the start and end vertex. And the way that I did that was to actually just store some information on the space mesh before we even do any of the separation, then just reference that later. So we'll store a named attribute. Actually, we'll store 2. So we'll call this top and bot. And once again, we can use the normal, and I'll compare this to +1. If we look at that and increase our epsilon, we'll see this becomes our selection for the top. So that's fine, I'll plug that in, and then I'll duplicate this, and we'll make this our bottom selection. We preview that, that's over there. I think that's fine. So it's basically going to be calculating these paths. It'll start over here and, for example, try to find the path. If our bottom is over here and our top is over here, it's going to try to find a path that goes along these to reach over there. So it might do something like this. So you might get something like this, and then if we subdivide the mesh before, for example, then maybe it might do something like this. So you want to just give yourself as many options as you can, but it also depends on your use case. Sometimes you don't want that many pipes, other times maybe you want more pipes. So yeah, that's your call. Another thing you can do is to plug these straight into the group input, and then just choose a vertex group instead, so that you can specifically paint where you want the algorithm to start and end. That might give you a bit more controllability in the shortest edge paths in your implementation. So we'll reference those 2 attributes. Let's call the top and bottom, put the top there, bottom there maybe, something like that. And then our last thing is this edge cost value. So add a random value, plug that in over there, and now when you change these and mess around with this, you'll get different patterns emerging. Once again, with more subdivisions, you get more intricate looking patterns. Cool, let's go with that for now. Okay, so this was edge paths to curves. So we've got curves out here. Let's turn those curves into a mesh. You can also use the curve to tube node, but I find this to be a lot slower. You can see that's 4 milliseconds, whereas the curve to mesh with a circle profile 8. Let me just change these to be the same resolution so that you can see exactly the time difference. Yeah, this takes 1.2 milliseconds and this is less than 1 millisecond. So let's increase this up to 32 just to see the difference. 0.12 milliseconds and 1.5 milliseconds. So this way is definitely faster, but you don't get these rounded caps and the baked in UV maps and all of that, which you might want. I think I did actually capture those myself, so yeah, that's going to be your call which one you want to use. I think let's just use the curve to tube because it gives the UV map here. And I developed this product in Blender 4.5, so I didn't have this node available. Okay, cool, so that gives us kind of pipes. The issue now is that there are in fact many pipes overlapping each other. Let me try to illustrate this for you. So if I use a random value with an index evaluated on the spline domain, so this is going to give me a random value for every spline, and let's just scale this on a normal just to show you. Look at that, there were 3 pipes overlapping each other, here's 3 overlapping each other, here's 4 overlapping each other, so there's a lot of overlap, a lot of wastage going on. We're using a lot more geometry than we need to. I'll just turn that off for a second and let's go into trying to clean this up. So first thing to do is convert these curves to a mesh. At the end we're going to convert the mesh back to a curve, so I'll just throw that in over there. But here, while it's a mesh, this is where we want to analyze and clean this up a little bit. So let's bring in a repeat zone, because we basically want to, for every single curve, we want to compare it to the other curves that are close to it and see which one is longer or which one is further along its curve. Whichever one is further along its curve, that's the one that we keep, and the others get deleted, so that if there's any shorter ones running on top of longer ones, they'll all just get deleted. So we'll plug this in over here, plug that out over there, and what I want to do is for every point that we go into, I want to sample the nearest point. So let's sample index, and let's actually capture from when it is still a curve. On every point we'll capture from the spline parameter. In my product I actually used factor, so let's see, we're sampling the factor of every of the nearest point, and then we're going to compare, is that factor greater than its own factor, and if it is, then we delete that point. So now if we go back to this, let's increase this to maybe 20 iterations, and there we see there's a few things happening, so something must be working. Turn this back on, and now we see that we have no doubles at all. If I bypass this one more time, you see all those doubles come back. So this repeat zone is definitely working. Let's just confirm that one more time. So curve to mesh over here, we have 101 vertices, but after the repeat zone we drop down to 58 vertices. Cool, so that removes weird shading artifacts and all of that stuff. Just gives us nice pipes. Okay, so now we can, let's mess around with the curve radius a little bit. Let's add a random value. Again, I'll evaluate this on the spline domain so that each spline gets a different value, and we'll go, let's say, between 0.5 and 1. I guess that's fine. Remember, you can add all of these parameters into your modifier stack so that you can customize these per object. Okay, I'll just add this in with the rest so that I can see what it's all starting to look like together. So now we see that these tubes are intersecting quite a lot with the geometry. So we need to push these tubes away, basically push them along the normal direction. And obviously we've been doing a lot of converting back and forth between curves and points over here, so the cleanest solution would be to just capture this normal direction before doing any of this stuff. So let's add a store named attribute. I'll call this NRM for normal, and then plug the normal in here, change this to vector, leave that on point. Now with our named attribute normal, we can scale this and put this into a set position offset. So just play with that. Yeah, we see that works nicely. Can get that clearance that we need. But if we want to make this truly procedural, we're going to see that these bigger tubes need to be pushed further away and the smaller tubes a little bit less so. So we are already giving them random values for that curve radius, so we can use that to affect how far it pushes away as well. Just add a scale node so that you can control exactly how much it scales by. And just like that, we see the small ones are now pushed away, but the big ones also pushed away enough. If you want, you can put this through a map range for some finer control. Just remember to uncheck clamp. And we'll go something like this. And that seems to work well enough. You're just going to constantly mess around with these until you get something that works. Okay, that seems good enough. Let me just play around with some of these things just to make this a bit nicer to look at. So remember our end vertex is at the bottom, so that'll be this one. Let's mess around with that. Okay, this isn't giving me many options, so let me just try circling this. Nope, not enough options, so let's just swap these two around. And okay, cool, that gives us something a bit nicer. And this is going to be something that you'll have to watch out for. Obviously we'll be subdividing the mesh twice, so these small faces end up getting quite a lot of pipes. You might want to again add this epsilon into your modifier stack and then assign a vertex group where you can custom paint and direct where all of these things should show up. Cool, I'll just give myself more space over here, and then after the set position we can subdivide this curve. Might not even need that, but you can leave it there as an option. Most importantly, we can add in a fillet curve node. I will set this to poly and check limit radius so that we don't get ugly artifacts, but this will be able to, with this we'll be able to bevel those corners and get something nice there. I think I'll turn off the subdivide curve for now. We can add resolution later if we need. Okay, so this one on poly with a count of 1 gives us those sharp 45-degree cuts, and then we can add another one with a count of 3 and make this radius much smaller, so that just rounds out those corners. Cool, I think something like that works. Another thing you can do over here is store a random value, and this will be helpful in the shader if you want to randomize materials and colors and stuff like that. Before we do our fillet curve, let's capture a random value. Once again, capturing the index on the spline domain, put that into the ID, change the seed, and from 0 to 1 should be more than enough. Plug that in over there. And let's add this pipes material, and then just to confirm that it works, we'll bring in an attribute node on the pipes material. Understand. Cool. Yeah, that works. But let's put this through a ramp. Change this to HSV and far. There you go. You can have random colors on every pipe. Okay, cool. That is the pipe network. And one more thing we can add to the pipe network are little buckles just going across it, kind of just to, add more detail, make them look a bit nicer from further away instead of just being boarding tubes. So, before the second fillet curve, so after this first one, this is where I'm going to branch off, and we'll go curve to mesh, and then merge by distance. You'll see that removes a couple of overlapping verts and edges, and then convert it back to a curve. And then with this curve, we can go curve to points. Now I'm converting it back to a curve and then to points because I want to capture something here from these curves, which we'll use later, but I'll show you that when we get there. So let me change this to evaluated, and we will instance on points. This is going to be a cylinder. You can change this to have 8 vertices and make this quite thin, 0.1. Change the radius to 0.1 and make the depth 0.03. We can tweak that just now to make sure that everything works nicely. Okay, I'll duplicate that join geometry and just put this over here, and let's set the material to this, give it that metal. Okay, so let's first try to handle the scale. You can see these are being instanced inside, but they are smaller than the pipes, so their scale needs to change with the radius of these pipes. And we can do that by setting the point radius of these points. Remember, we went from curve to points and then instance on those points. So we change that radius and then plug that radius into the scale over here. We should be golden. I'll just plug that in there for a start, and now we need to get this radius from earlier on in the node graph where we actually set that radius. We can see that over here where we set the curve radius. So let's go after the set position. We've got this capture attribute node, so let's just also capture the radius, and then I'm going to feed that radius all the way over here. Let's clean this up a bit. Okay, so that radius goes. You can see that it mostly works. Those are now starting to peek out the edges. Now we need to align these, so let's align them to the tangent over here. Align rotation to vector. That's in the vector. That's the rotation. Cool, that works. So now we just need these to be a little bit bigger, just a little bit. You can add in a multiply and just multiply it by like 1 point a little bit. Okay, then another issue is these ones on the corners with this fillet. These are going to have to move based on how much we fillet these corners. For example, if I turn the second fillet off, you'll see that they're kind of okay where they are, but as soon as we start filleting those bends, we're going to need to offset these so that they go further in. So let's add a set position node after the set point radius node, and this is going to be a little complicated, but this is the math that I found that works. So I'll calculate the cross product between the tangent and the normal. This basically gives us if the tangent is facing this way and the normal is facing this way along the y-axis, then the cross product will give us this vector pointing up, which is 90 degrees to both of those, or all of those. So we'll cross product those two, and then I'm going to vector rotate that. I'm going to rotate that vector around the tangent by 90 degrees. This is going to be the vector that I scale and apply to the offset we're also only going to apply this a little bit, and you'll see that that pushes it inwards by that tiny amount, so that centers those ones, makes that look nice. Also, now if we do increase these or increase this rounding, now we have a small little slider here to just nudge those further back into place. Okay, cool. So another thing is we see that these are placing these buckles at the end of the pipes, which I don't necessarily want, so I'm going to omit that from the selection. Before we convert it into a curve, I'll capture another attribute. We'll look at, or before we could convert it to points, sorry, while it's still a curve, we'll look at the endpoint selection. So we've got a start and end size of 1, so that means that the selection is going to output both the start and end. Let's put this through a not boolean so that only all the other points are marked as true, and then we'll plug that into the selection. So now that removes our instances from the edges there, from the ends of the curve, and we'll see some of these overlapping ones over here. We can just increase this merge by distance by a little bit, and that'll take care of that. Cool, and that's about it. Like, there's, you know, a couple of other things that I did, adding switches, a whole bunch of switches, like whether to turn on and off the pipes. I added a realized geometry right at the end here so that you can apply the modifier and turn everything into actual geometry. So like if I show you, if I apply this now, only some of the stuff gets stays, all of the instances don't. So we'll just realize instances over here, and then when you apply it, it's all real geometry for you to mess around with and, you know, continue working on further. Okay, and that's the end of the tutorial. Thank you very much for watching. I hope this is useful to you guys, and I hope that you make some really cool things with it. Please, you know, leave a comment, leave a like if you enjoyed this, and tag me on Instagram if you make anything using this. You know, I'd like to see what you guys come up with. Yeah, cool. Until next time.